BYD just built a car with no battery pack. Not a smaller one, not a hidden one, no separate pack at all, because the body of the car is the battery. Every structural panel, every floor section, every load-bearing surface stores energy and holds the car together at the same time. And here is the number that stopped the room cold at their March 2025 reveal. 10% to 70% charge in 5 minutes. You heard that right, 5 minutes. That is less time than most people spend in a gas station convenience store, and it adds roughly 250 miles of range. But the charging speed is not even the most important part of what BYD built. And that is just the beginning. Because the architecture that makes 5-minute charging possible also makes the car structurally stronger, lighter, and more efficient all at once. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you are going to understand exactly why this architecture, not the speed, not the range, is what rewrites the electric vehicle blueprint permanently. To understand why, we need to start with the technology it replaced. The modern electric vehicle battery pack is one of the more elegant engineering solutions of the last 30 years, and it deserves to be understood before it gets criticized. Engineers did not arrive at the flat floor battery box by accident. They arrived at it by solving a genuinely hard problem. How do you store enough energy to move a 2-ton vehicle 250 miles, keep it safe in a collision, protect it from heat and cold and moisture, and still sell the whole thing at a price someone will actually pay? The answer they landed on was modular. You take individual battery cells, small, cylindrical, or prismatic, each storing a modest amount of energy, and you group them into modules. You stack those modules into a large flat pack. You enclose the pack in a rigid protective casing, bolt it to the underside of the vehicle's floor, and engineer the rest of the car around it. The pack sits low, which keeps the center of gravity close to the ground. That improves handling. It also keeps the heavy mass away from the crumple zones at the front and rear, which helps with crash safety. Engineers love this architecture because it is modular. You can tune the pack size for different vehicle ranges without redesigning the whole car. Manufacturers love it because the supply chain is established. Cells come from suppliers. Modules get assembled in a separate facility. Packs ship to the final assembly line. Governments love it because it is testable. Regulators can certify a battery pack as a discrete component with defined safety standards, which maps cleanly onto existing approval frameworks. Now, here is the part that most people never think to ask. For all the elegance of that solution, nobody ever seriously questioned whether the battery pack and the car body had to be two separate things. The question sounds almost naive once you say it out loud. Why did no one push on it sooner? The honest answer is that the industry grew up around internal combustion engines, where the fuel tank is always a separate vessel, a steel container that holds liquid, gets mounted somewhere, and connects to the engine through a line. The battery inherited that mental model wholesale. It became a vessel, a box, a thing you put somewhere and build around. That mental model held for decades because the engineering trade-offs genuinely supported it. A replaceable, certifiable, testable pack made sense when battery technology was young and standards were still being written. The system was not broken. It was rational. The only question was whether it was still the best way, and that question had a buried answer nobody wanted to look at too closely. The status quo was brilliant. What it was hiding was something else entirely. The buried flaw in the modular battery pack is not one dramatic failure. It is a quiet, compounding inefficiency that gets worse the more you try to improve performance. And it starts with a number that sounds mundane until you follow the math. In a conventional electric vehicle battery pack, somewhere between 40 and 50% of the total volume is not battery cells. It is everything else: the casing, the structural foam, the cooling channels winding between modules, the wiring harnesses, the thermal management layers, the brackets and fasteners holding modules in place inside the outer shell. Not structural material, not energy storage, not safety geometry. It is packaging, and packaging alone. Picture a moving box. You pack it carefully, but between the bubble wrap and the cardboard dividers and the padding around fragile corners, the actual objects you are moving take up maybe half the space. The box is doing its job, protecting the contents, but half of what you are carrying is dead weight. A conventional battery pack works the same way. You are hauling a significant amount of engineered packaging, and that packaging does exactly one thing. This is not about one inefficient component. It is about a design constraint that forces every other system on the vehicle to compensate. The pack is heavy. A typical pack in a mid-size sedan weighs around 1,000 pounds, roughly the same as a grand piano, and the car's frame has to be engineered to carry that mass without that mass contributing anything structural in return. You get all the weight penalty and none of the rigidity benefit. Here is what that cascade looks like in practice. A heavier pack demands a stronger, heavier floor structure to support it. A heavier vehicle needs more energy to accelerate and maintain speed. More energy demand requires a larger pack. A larger pack adds more weight. The loop feeds itself, and every iteration pushes the vehicle further from efficiency. Engineers put a precise name on this: parasitic mass growth. Each kilogram added to manage the battery requires approximately 1.3 additional kilograms elsewhere in the vehicle to compensate. At pack scale, that number compounds fast. The thermal problem layers on top. All that packaging has to be penetrated by cooling channels to keep the cells from overheating during fast charging. The more complex the cooling network, the more mass added for thermal hardware, the more points of failure introduced. In 2021, BYD's engineers began answering that question with data that was harder to dismiss than anything the field had seen before. The team behind what became cell-to-body technology was not a skunkworks group hidden from the rest of the company. It was BYD's Advanced Battery Structure Laboratory, the same division that had developed the Blade battery. Working in close coordination with their vehicle architecture group in Shenzhen, under a program internally designated as the Integrated Energy Structure Initiative. The core idea sounds almost too simple once you hear it. What if the top face of each battery cell became the floor of the passenger cabin? Not metaphorically, structurally, literally load-bearing. Previous attempts at structural battery integration had run into the same wall. You can bond cells to a chassis member, but bonding creates stress concentration points, places where two materials with different thermal expansion rates are glued together and asked to survive decades of vibration, temperature cycling, and mechanical load. When temperatures swing, the bond fatigues, the interface cracks, the cell shifts. Earlier structural battery experiments in European and American research labs had demonstrated the concept in short cycle tests, but could not survive the 100,000-mile durability standard that production vehicles require. Here is what those earlier programs got fundamentally wrong. They were trying to attach the battery to the structure. BYD's team inverted the problem entirely. Instead of bonding cells to a separate structure, they eliminated the separate structure. Think of a honeycomb panel, the kind used in aerospace bulkheads, where hexagonal cells of thin aluminum are sandwiched between two face sheets. No single cell is very strong, but the geometry distributes load across thousands of walls simultaneously, and the whole panel becomes extraordinarily rigid. BYD applied that same geometric principle to their blade cells. The cells are long, flat, and thin, packed side by side with their top surfaces aligned, forming a continuous load-bearing surface the way a wooden floor does. Individual boards are not especially rigid. Lock them edge to edge across the full width of a room, and the assembly becomes a platform you can build a house on. The cooling channels stopped being packaging weight. They became structural geometry. The cells cannot simply be exposed structural members. They still need thermal management. BYD integrated the cooling channels directly into aluminum extrusions that also serve as lateral stiffeners. Every gram of material now does at least two jobs: storing energy and physically reinforcing the floor. That is not an incremental improvement over what came before. It is a different category of engineering. The question was how that translated into real performance numbers when they put it in an actual car. Before describing what the cell-to-body architecture achieves, it is worth being direct about where it still falls short, because the honest picture is more interesting than a clean victory lap. The integrated design makes individual cell replacement significantly more complicated than in a modular pack. In a conventional pack, a degraded module can be swapped out at a service center without disturbing the rest of the vehicle. In a cell-to-body system, the cells are structural members. Accessing them requires partial disassembly of the floor. That raises long-term maintenance and repair costs, and it is a genuine consideration for buyers thinking about a vehicle they plan to keep for 15 years. But here is what that number actually means in practice. The vast majority of electric vehicle battery degradation happens gradually and predictably over the full life of the vehicle, not in localized module failures that require mid-life swaps. Independent studies of lithium iron phosphate cells, the chemistry BYD uses, consistently show capacity retention above 80% after 200,000 miles of use. For most buyers, the maintenance complexity of individual cell replacement is a theoretical concern, not a practical one, over a realistic ownership horizon. Where the architecture delivers unambiguously is in structural stiffness. BYD's own measurements, cross-referenced against standard industry torsional rigidity tests, show the cell-to-body platform is roughly 70% stiffer than their previous modular pack vehicles. 70%. That puts it in the same stiffness range as vehicles built with carbon fiber reinforced polymer chassis structures, the kind of engineering that shows up in sports cars costing $300,000. BYD reached those numbers not with exotic materials, but with geometry, the cellular load-sharing principle that makes the integrated floor act as a single unified panel, rather than a box sitting beneath a separate frame. Not a component improvement, not a chemistry upgrade, a complete rethinking of what a vehicle floor is allowed to do. The non-obvious application where this already wins today is cold climate freight. Electric delivery vehicles operating in northern Canada and Scandinavia have historically suffered severe range penalties in winter because the battery management system burns stored energy just to keep cells warm enough to function. The cell-to-body thermal integration maintains cell temperature more efficiently, precisely because the structure surrounding the cells is also the thermal management network. There is no gap between the heat source and the thing being heated. The question was no longer whether cell-to-body worked. The question was where it would go first and how fast. The first production vehicle to carry the full cell-to-body platform was the Han L sedan, which began deliveries in China in mid-2024. Field monitoring data collected from the Han L fleet over the first 6 months confirmed what the laboratory had projected. Torsional rigidity held within 2% of factory specification across vehicles that had accumulated over 30,000 miles of mixed urban and highway use. Range figures recorded in real-world driving averaged 580 kilometers, approximately 360 miles, under normal mixed conditions, tracking within 4% of the rated figure. The field matched the forecast. Why does that matter? Because laboratory results in automotive engineering are notoriously optimistic. The controlled environment that produces a clean stiffness number does not replicate the thermal cycling of a northern winter, the vibration spectrum of a potholed city road, or the sustained load of a fully loaded vehicle on a long-distance highway run. When field data from a large real-world fleet tracks closely with laboratory prediction across all of those variables, it signals that the design is genuinely robust, not just impressive in ideal conditions. The manufacturing compatibility detail that mattered most was this. BYD built the cell-to-body floor assembly on existing production lines with modifications rather than entirely new facilities. The aluminum extrusion process for the integrated cooling and stiffener members was adapted from aerospace supplier tooling already in use in China's rail sector. That lowered the capital cost of scaling the platform significantly compared to what a purpose-built greenfield line would have required. A senior structural integration engineer involved in the platform's development noted that the most significant validation was not the stiffness number itself, but the consistency of that number across vehicles built on different shifts across different plants, a sign that the assembly process had been genuinely industrialized rather than hand-tuned for the launch batch. Field monitoring data from the Han L fleet has been made available through China's public electric vehicle safety reporting database, which logs aggregate performance metrics across registered new energy vehicles quarterly. If the idea that a battery and a car body can share the same physical material surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one application where structural efficiency mattered more than repairability. Then it spread outward from there. The claim now had receipts. More than 300 international patent families now cite BYD's cell-to-body structural integration filings as prior art. These are not academic citations. These are legal and financial commitments. Companies paying attorneys, filing fees, and engineering hours to stake out territory adjacent to the core technology because they believe the platform will define a competitive battleground worth defending. The patent geography tells its own story. Filing concentrations are highest in Germany, Japan, South Korea, and the United States, the 4 countries whose automotive industries have the most to lose if this architecture becomes standard. When competitors file defensively around your core patent, it is one of the cleaner signals in industry that they believe you have built something real. Here is what most people get wrong about the corporate response. It is not cautious interest. It is a full-scale engineering mobilization. Volkswagen Group announced a dedicated structural battery integration research program in late 2023, with committed funding of approximately €2 billion through 2027, specifically targeting the cell-to-body architecture as a design reference point. Toyota's Advanced Research Division filed more than 40 patents in 2024 related to structural cell bonding and integrated thermal management, the 2 specific technical problems that BYD's platform solved. Panasonic announced a joint development agreement with a European chassis manufacturer in early 2024 to explore integrated cell structure formats. And CATL, BYD's primary domestic competitor, launched their own structural battery platform called Freevoy in 2024, explicitly positioning it as a direct response. The regulatory driver accelerating adoption in the European market is the Euro NCAP Safety Framework Update, scheduled for 2026, which introduces new requirements for cabin integrity under lateral load, a test that integrated structural battery floors perform exceptionally well on by virtue of their geometry. That single regulatory change is expected to make cell-to-body architecture a structural advantage in the European safety rating system, not just an efficiency feature. In any market where vehicle structural ratings directly influence consumer purchase decisions, which describes virtually every mature automotive market, a 70% stiffness advantage is not a trend. It is a competitive pressure no serious manufacturer can afford to ignore for long. The open performance data from BYD's Han L fleet, cross-referenced against the Chinese National EV Registry's quarterly safety reports, is publicly accessible and has been independently reviewed by automotive research groups at Tongji University in Shanghai and the Technical University of Munich. Scale projections for cell-to-body adoption across BYD's own lineup suggest that by 2027, the platform will underpin vehicles accounting for more than 40% of the company's total annual production volume, which, at BYD's current sales pace of over 4 million vehicles per year, means more than 1.5 million cell-to-body vehicles entering service annually from a single manufacturer. 1.5 million. That is roughly the entire annual passenger vehicle sales volume of Australia. The secondary benefit that gets less attention than the performance numbers is material efficiency. Because cell-to-body eliminates the module housings, pack casings, and structural foam layers of a conventional pack, the total quantity of steel and aluminum used per vehicle drops meaningfully. Early life cycle assessments estimate a reduction of approximately 80 to 100 kilograms of structural material per vehicle compared to an equivalent modular pack design. Across 1.5 million vehicles annually, that represents somewhere between 120,000 and 150,000 metric tons of steel and aluminum per year. Simply not needed, not manufactured, not shipped, not recycled. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. The repair ecosystem is the most immediate obstacle. Fewer than 3% of independent automotive repair facilities globally have the tooling and training to work on integrated structural battery systems. That number needs to increase by an order of magnitude before cell-to-body vehicles can be owned confidently outside major metropolitan areas with authorized dealer networks. The insurance industry has not yet developed actuarial models for structural battery damage in low and moderate speed collisions. Without standardized repair cost data, insurers in several markets are applying precautionary surcharges that meaningfully increase the total cost of ownership, offsetting some of the efficiency gains that technology delivers. Recycling infrastructure for integrated cell-to-body assemblies is nascent. Conventional pack recycling separates cells from structural materials at the module level. Cell-to-body assemblies require new disassembly protocols, and the industrial capacity to process them at scale does not yet exist in most markets outside China. Raw material supply for lithium iron phosphate cells, while more geographically distributed than nickel or cobalt chemistries, still concentrates lithium processing capacity significantly. The two largest lithium carbonate processing operations serving the LFP supply chain are both located in China's Qinghai province, a single region the size of Texas. Diversification of that processing capacity is a multi-year infrastructure build-out, not a policy decision. Here is the detail most analyses skip entirely: standardization. For cell-to-body to spread across manufacturers, the industry needs shared dimensional and interface standards for integrated floor systems, the way USB standardized data transfer across devices made by dozens of competing companies. No such standard currently exists, and the patent landscape makes neutral standardization politically complicated. The International Electrotechnical Commission has a working group addressing this, but published standards are not expected before 2028 at the earliest. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem, as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the transition demands is a different question entirely. The story of cell-to-body technology is ultimately the story of what human civilization can build and where it can build it. every major shift in how vehicles store and use energy has expanded the geography of mobility, the places people can live, the distances they can work across, the communities that stop being remote. This shift is no different, except that it arrives at a moment when the stakes attached to how we power transportation have never been higher. The equity dimension is easy to miss when the conversation stays at the level of flagship sedans and luxury launches. The markets with the most to gain from affordable, long-range electric vehicles are not Western European cities with mature charging infrastructure. They are secondary cities in Southeast Asia, Sub-Saharan Africa, and South Asia, where the cold chain collapses because delivery vehicles cannot reliably cover rural routes, where air quality in dense urban centers is driven significantly by internal combustion fleet density, and where the cost per mile of transportation is a meaningful fraction of household income. The same efficiency gains that enable 600 miles of range in an expensive vehicle enable 250 miles in one that costs a third as much to manufacture. What is genuinely new, not incrementally better, but categorically different, is a vehicle architecture where the energy storage system and the structural system are a single unified object, each making the other more capable simply by sharing mass and geometry. That is not a minor improvement. It is a different category of solution. The researchers and engineers who developed this platform gave the world a tool. Whether the world picks it up at the speed the energy transition demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. When the geometry of how a vehicle stores energy changes, every system built around that geometry changes with it. Suspension tuning, crash structure design, thermal management, manufacturing logistics, insurance frameworks, repair training, recycling protocols, all of it recalibrates. That recalibration is disruptive in the short term and generative in the long term, because it clears space for solutions that the old geometry made impossible to imagine. If the question of what cell-to-body means for how we power vehicles raises a question about what powers the cells themselves, about what happens when the chemistry inside those blades changes as fundamentally as the structure around them did, that story is worth understanding too, and it is the subject of our next video. China's new sodium battery will change electric vehicles forever. The link is in the description. If this changed how you think about what an electric vehicle actually is, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you in the comments. Is cell-to-body a genuine architectural leap that will define the next decade of electric vehicles? Or is it a manufacturing advantage that only works at BYD's scale and never fully escapes it?